All right, so let's take a look at section 8.4. Right, so as I said, yesterday we learned how to multiply and divide using trig form of complex numbers. Now we're going to learn how we raise to a power. Okay, the reason why we want a way to raise to a power, we already have a way to do it in rectangular form. So like if you had something like 1 plus 2i, and I wanted you to square it, well, it's not that hard to really do. We just have to FOIL it out, and we get 1. And then when we distribute, we'd have 2i, another 2i, it's 4i. And then 2i times 2i would be 4i squared. Well, I squared is negative 1. And then when we combine like terms, that's what you get. If you took 1 plus 2i and squared it. We did that back when we learned complex numbers. Well, squaring it's not bad. What if I asked you to do something like this? Now you have to write 1 plus 2i 5 times. And you have to distribute each one of them. Get the answer, distribute it to the next one. Get the answer, and keep going. All right, it's going to start to get time consuming, and we want a better way to do it. And even worse, if I gave you something like this, well, you can't do that by hand. Right? You can't multiply this out, foiling, distributing 378 times. Okay, there's not enough time, you probably make a mistake. Well, the method I'm going to show you relies on having this number in trig form. And it doesn't matter if this number is 300 or 3 million. It's just as easy, right? Once we learn how to do it in trig form. Okay, but first we got to kind of see what the pattern is. See if we can figure it out. So first thing I'm going to do is just rewrite my complex numbers z squared as z times z. So I'm going to write it out. Okay, and if you think of this as multiplying 4 things together, we could use the commutative property, rewrite it. Let's put the r's next to each other, and we're going to multiply them in the same step. So James, if I put the 2 r's next to each other and did that out, what's r times r? R squared. Okay, and now I still have the rest of it. Cosine theta, I sine theta, cosine theta, I sine theta. Now we're going to use the distributive property. Okay, multiply all that out. Cosine times cosine. It's cosine squared. Cosine times I sine. Cosine times I sine. I'm going to have 2 of those. 2 of the, let's write it like this. I sine cosine. And the last part is I sine times I sine. Well, I times I is I squared. That's a negative 1. And then sine times sine, sine squared. Okay, so all I did was distribute it using either FOIL or double distributive, whatever you call it. Any questions so far? That's pretty much it. I'm going to regroup it, and then from there we need to recognize 2 identities. Okay. I'm going to move minus sine squared next to cosine squared. So it's going to be cosine squared minus sine squared. And then I'm going to put this other part second. Plus, I'm going to switch the 2 in the I to help you see the identity a little better. 2 sine cosine. All right, so now this is something, and this, oops, is something else. Okay, anybody remember what either cosine squared minus sine squared is? Careful, it's not cosine squared plus sine squared. That's a trig identity equal to 1. Okay, but this isn't plus, this is minus. Or does anybody remember what 2 sine cosine is? Yep.
The first one is cosine 2.
Good. Excellent. And do you know the second one? Okay, using it's going to be very similar to the first one. Anybody have a guess what that identity is? 2 sine cosine? Sine what? Like that? Not quite. Sine. Darren, can you help him out? I'm not seeing this. There's going to be like a symmetry to each one of these. I lost something in this. Theta, yeah. These are double angle identities. We did these back in section 7.5. The cosine ones, I think some people forget because there were 3 versions of it. But this one, I hope, usually is the one that people remember because it's the only one for sine. So sine 2 theta is 2 sine cosine. Right, so that's how you get z squared. Right, now looking at this, without going through it again, want to see if we can get z cubed. So that would be like r cosine theta plus I sine theta written 3 times. Anybody have a guess what the radius would be? Yep. Yep, it would be r cubed cosine I sine. And how about my angle? Yeah?
Would it be cosine 3 theta plus I sine 3 theta?
Yeah. So using just kind of our pattern ability here, we would hope that's what it would be, and that's what it is. If you raise something to the 5th power, it'd be r to the 5th cosine 5 theta, I sine 5 theta. Right? So the trick here, this is actually a theorem. We're not going to prove the theorem. Okay? What we just did is we proved it for one case when you square something. We're not going to prove it for everything. But it's called DeMoivre's theorem. Okay? DeMoivre's theorem. So let n be any integer you want. And what's below it here has to be a number in trig form. That's the key. To use DeMoivre's theorem, you have to write your number in trig form with r and theta. Well, to raise a number to the nth power, take your radius, raise it to the nth power. That's something you can just type in on the calculator. Take your angle and multiply it by the power. Okay, 2 very simple operations, but now I think the hard part is keeping it straight with what we learned yesterday. So you got to remember your rules for multiplying numbers in trig form, dividing numbers in trig form, and raising numbers in trig form to a power. 3 separate things. Okay, even if you had something like this, and you said, oh, well, it's not in trig form. I got to change 2 plus 3i to be in trig form first. I guarantee you, it's going to be faster to change this in trig form and then use DeMoivre's theorem than write 2 plus 3i 12 times, 12 sets of parentheses, and do all the distributive properties. It's going to be much faster to use this. Now, if you only had to square that, maybe cube it, maybe some people could do that a little faster. Squaring, I think certainly people could do that part in their head. This would slow you down. But for anything higher than powers of 3 or 4, DeMoivre's theorem is the way to go. It saves you time. Okay, so this one's kind of on the border, whether or not we use DeMoivre's theorem, but let's try it. It's 1 plus root 3 I. Cubed. Okay, I want to cube that using DeMoivre's theorem. Now, before I can even use DeMoivre's theorem, Alex, what's the very first thing I got to do with 1 plus root 3i?
get it into trig form?
Yeah, get it into trig form or polar. What are the two letters we need to find in trig form? Yep, we need R and we need theta. So this part is what we learned yesterday. So let's go through it real quick. Okay, first thing I'll do is find R. Use the Pythagorean theorem. Square root of 3 squared is 3. 1 squared is 1. 3 plus 1 is 4. Take the square root. 2. Okay, so my radius is 2. And my angle. Brianna, what's going to be the formula for my angle?
The inverse tangent of square root of 3 over 1.
Yep, square root of 3 divided by 1. So we'll just write the square root of 3. So second inverse tangent of square root of 3. And, whoops, inverse tangent. Maybe that's what you did, Darren, when you said you got like a different number. Maybe you did regular trig function instead of inverse. I don't know. But yeah, so inverse tangent, we get an angle of 60. Okay, so now I've got my number that I want to cube in trig form. So 2 cosine 60, I sine 60. Remember, you're cubing the whole thing. So let's start with my radius. James, what's my radius going to be? Okay, how do you get your radius using DeMoivre's theorem? Yeah. So 2 to the 3rd power is how much? That'd be 2 to the 4th power, 16. 8. Yep. So 8 cosine, I need my angle. Okay, Jill, how do I get my angle? And what do you do with the 3 and the 60? You take them and multiply them. Yep. So take your angle, multiply it by the power. That's the shortcut. And 60 times 3 gives me 180. Now, if you get an angle that's not a quadrantal angle, we'll generally leave it as the answer. But when you get angles that are 0, 90, 180, or 270, we can do it out. Okay, so let's do it out and see what we get. Okay, quadrantal angles give you answers that are like 1s, 0s, and -1s. So we're going to get a nice answer. Cosine of 180. Let's do it in degrees. -1. Sine of 180 is 0. Well, in this case, I times 0, the imaginary part disappears. And I'm just left with 8 times -1. So when you take and cube 1 plus root 3i, the answer is -8. Won't always come out nice, but this time it did. Any question on that? All right, let's try this one. This would definitely not be one you want to try to do the way it's written, because now you're raising it to the 8th power. Okay, so Victoria, what are the 2 things I need to change this into trig form?
The radius and theta.
Yep, I need the radius and theta. And what theorem do we use to get the radius? Good, Pythagorean theorem. This time we're going to be in quadrant 2, left and up. Left, up. Okay, this side is root 2 over 2. This side is root 2 over 2. I think we had to square numbers like this in the homework. I think we just did one. So r squared equals root 2 over 2 squared. plus another root 2 over 2 squared. We'll square it. Casey, do you remember what we said when you square root 2 over 2? What do you get? Yep, you get 2 over 4, which is a half. Perfect. So r squared is 1. Take the square root. Your radius is 1. Okay, your angle. You could use the inverse tangent of y over x, but remember in quadrant 2, you got to add something to it. Anybody remember what number you have to add to it in quadrants 2 and 3? Yep.
The 180.
You got to add 180 or pi in radians. Or we could just be kind of clever and look at the kind of triangle we have here and know that that quadrant makes a 90. What kind of triangle is this?
45, 90.
Right, it's a 45, 45, 90. We know it's a 90, and it's isosceles. So this has to be a 45. So now the question is, what is the angle from there to there? How many degrees would that be? Emily?
I don't know.
Well, how many degrees from there to there?
90.
90? And then how about from there to there?
Oh, 45.
45. So altogether?
135.
135. Okay, in my head, if I know I got a 45-degree angle in quadrant 2, it's faster for me to think of 90 plus 45. If that's confusing, then go back to using inverse tangent of y over x. Just make sure you add 180 because you're in quadrant 2. Okay, so now we got our angle. Let's write it out. 1 cosine 135. And raise it to the 8th power. Okay, so Cole, how do I get my radius? We're going to raise what to the 8th power? 1. And 1 to the 8th power is, it stays the same. So my radius is still 1. Now I need my angle. Darren, how do I get my angle? Think about what DeMoivre's theorem says. You take the 135 and multiply it by 8. Okay, let's do that here. So I get 1,080. That's a pretty big angle. What can I do to make that angle smaller? Because when I write my answer for an angle, I want it between 0 and 360. I don't want an angle that's up in the thousands or negative thousands. Yep?
You subtract 360.
Yeah, subtract 360. So I get an angle of 0. Again, that's a quadrantal angle, so we should do it out. Okay, really, we should have these memorized. Cosine of 0. Okay, cosine of 0 is going to give you 1. Sine of 0 gives you 0. And it just happens, again, the imaginary part disappears. And we're left with 1 times 1. Or just 1. Right, so if you take what we had originally, raise that to the 8th power, you just get 1. Yeah.
How do you get 135?
135. So we have a 45, 45, 90 in quadrant 2. You could think of that 45 degrees as a reference angle. And you could think of it as 180 minus the reference angle. That's how you get your answer in quadrant 2.
But I had to add 180 somewhere.
Well, that's a different way to think about it. So if you use the formulas I gave you yesterday, it's the inverse tangent of, it'd be negative 1 in this case, because this would be a negative, because it's going left. So y over x, divide them, you get negative 1. If you do the inverse tangent of negative 1, that's what you're going to get, negative 45. then add 180, you can get the same thing. So it's just different ways of thinking about it. Most people, I think, would just go back to the formula we learned yesterday. But, oops, inverse tangent. In my head, if I know this is a 45-degree angle, and I'm in quadrant 2, that's an angle of 135. If you had a 45-degree angle in quadrant 3, without even doing any arithmetic, I know it's 225. Because it's 45, plus I went halfway around. So it's 180 plus 45. If you had a 45-degree triangle in quadrant 3, it's 315. Because you're 45 degrees shy of going all the way around, which is 360. Okay? If you don't memorize them, that's okay. It just speeds it up a little bit. Okay, any other questions on that? All right. So looking at our first example, we cubed a number. Took something and we cubed it. What would be the opposite of cubing? How would you undo cubing? James?
You would take a third root or something.
Yeah, it's called the cube root. Yep. To undo cubing, you take a cube root. All right, so I'm going to go back and look at that. Let's see if I can get it all on the board. So if you take 1 plus root 3i and cube it, you get negative 8. What would you get if you take the cube root of negative 8? Okay, that is one answer. What would be another answer? It's kind of like saying if I took 2 and cubed it, I get 8. And then I said to you, what's the cube root of 8? Well, look back at what you started with, 2. Right? So if we took 1 plus root 3i and cubed it and got that, what do you get if you cube root this answer? Yeah? Yeah, if you cube root this, you change it back to what it was. 1 plus root 3i. Right? So this is one of the cube roots of negative 8. Negative 2 is another one. Okay? Turns out there are 3 cube roots of negative 8. I'll mention that later. All right? So if you take the cube root of negative 8, one of the answers is the thing that we cubed, 1 plus root 3i. In fact, that's how you can prove something is a root of something. If I said to you, prove to me 3 is the square root of 9, take 3 and square it. If you get 9, then you just proved it. Okay? If I said, prove to me 5 is the square root of 25, take 5 and square it. If you get 25, you just prove to me that 5 is the square root of 25. Or at least one answer. Okay, there will be multiple answers. Okay, so in general, we're going to find nth roots. Okay, and to find an nth root, this is the equation you need to set up and solve. Z to the n equals a. If it seems confusing, look at it with actual numbers. Let's find the square root of 16. Okay? Let's fill in 2 for n, 16 for a, and then I'll show you how this makes sense. So z is what you're solving for. Okay? You don't know that. N would be 2 in this case. A would be 16. So if you want to find the square roots of 16, if you can solve this equation, you can answer my question. Solving this equation will give you the square roots of 16. Now we just need to know how to solve it. This one is simple. Take the square root of each side. And you get 2 answers, 4 and negative 4. If they ask you to solve specifically for the nth roots of something equal to 1, Another name for that is finding the nth roots of unity. That's all that unity means. They want you to specifically find the square roots of 1 or the cube roots of 1 or the fifth roots of 1. Okay, so sometimes you might see this word in your book. It's just the special case when A is always 1. Okay, so the next part is how do you find nth roots? Okay, the process I'm about to write down is going to look confusing. All right, there's a lot of variables in it. When we do an actual example, most of these variables all become numbers, and it looks a lot easier. So I'm going to try to show you the general process, and then don't get too overwhelmed, because I think an example will make it much easier. All right, so we already said if you want to find the nth roots of a number A, that's the equation you need to set up. Remember, Z and A can be complex numbers. You do not have to get real answers here. You can get imaginaries. Okay, so complex. So the first thing we're going to do is rewrite Z to the n equals A in trig form. Well, let A equal R1 cosine theta 1 plus I sine theta 1. And let Z equal some other complex number. R2 cosine theta 2, I sine theta 2. So I just took Z and A, rewrote them in trig form. Each of them will have a radius. Each of them will have an angle. But the two radii and the two angles don't have to be the same. That's why I use theta 1 and theta 2, R1 and R2. Okay, next, what I'm going to do is take the equation Z to the n equals A and substitute in. I'm going to change A, the right-hand side, to what A equals. And I'm going to change Z, what's on the left-hand side, to what Z equals. So when I make that substitution, that's what I have now. On the right, when you're doing a real problem, R1 will be a number. Theta 1 will be a number. N will be a number. The only thing in this whole problem that you see here that's going to be letters, the R2, that'll be a variable, and theta 2, that'll be a variable. Everything else is going to be numbers. Okay, the reason we did it in trig form is because that makes the left-hand side very easy to do. Use DeMoivre's theorem. So you're going to have R2 to the nth power and theta 2 times the n. Okay? I kept the right-hand side the same. So I did out the left-hand side using DeMoivre's theorem. And a lot of times in problems, people will jump right to the second step. They'll just do out the nth power in their head, remembering I raise r to the power, and I multiply the angle by the power. And as far as our equation, that's pretty much it. Now, somehow we've got an equal sign between these left and right-hand sides. So what's on the left has to match what's on the right. That's the definition of equals. So you have a radius on the left. That's going to have to match a radius on the right. So solving that equation will give you r. In this case, R2. When we do a real problem, we're not going to have two r's and we're not going to have two thetas, so we'll just be able to use r and theta. You won't need the subscripts, because we're not going to have this many variables. And the angle on the left has to match the angle on the right. So n theta 2 has to match theta 1. If these things don't happen, what's on the left and what's on the right wouldn't be equal. Now, we used this idea earlier. N theta 2 could match theta 1 Or what could you add to theta 1 that wouldn't change it? I think we did it with subtracting in one of the problems because the angle was too big and we made it smaller. What can you add or subtract to an angle? 360 degrees? How about in radians?
2 pi.
2 pi. So n theta 2 has to match theta 1 or any angle that's coterminal with it. Okay, so n theta 2 will equal theta 1 or anything that's coterminal with theta 1. Okay, coterminal means same initials, same terminal sides. So when you do roots in trig form, there will be only one answer for r. You're going to get a single answer for the radius, but you're going to get multiple answers for the angle. N is going to be a number. So the only variable in this final equation is going to be k. The angle can have multiple answers. Just like a square root has multiple answers. It has 2. Well, a cube root will have 3 answers. A 4th root would have 4 answers. A 10th root would have 10. So whatever root you're finding, you need to find that many answers. And the way you're going to find all the different angles is you're going to let k take on different values. Okay. Starting at 0 and going up to n minus 1. So for example, if you wanted to find all the angles and you were doing a cube root problem, there's 3 answers. You're going to let k equal 0, 1, 2. There's your 3 answers. If you're doing a 5th root problem, okay, you're looking for 5 answers. To find all 5, we do k equals 0, 1, 2, 3, 4. So notice for a 5th root, I'm only going up to 4 with k because I'm starting at 0. That's important. Okay, I think it'll make much more sense once we do an example. Okay, and I said here that all the answers have the same value for r. So you can think all these answers, if you were to visualize them on like that polar graph paper, they're all the same distance from the center. In fact, they're all evenly distributed on a circle. So if you had polar graph paper, let's say you were doing a 4th root problem. You'd get 4 answers. They would all be the same distance from the center, all the same value for r, and they would all be 90 degrees apart. So what you'd really be finding is the vertices of a square. Okay? If you were finding cube roots, you're going to get 3 answers, and they're all evenly distributed. So you'd be finding the vertices of an equilateral triangle. If you were doing a 5th root, you're going to find 5 answers, and they would be the vertices of a pentagon, a regular pentagon. We're not going to spend a lot of time graphing, but some people like to visualize it. So if you like to visualize it, all the answers are going to be evenly spaced on a circle. All right, so let's try an example. Okay, this first one does not have to be done using the method I just showed you. This is factorable. You could bring the 1 to the other side. Okay, I'll just show you how you'd factor it. It's not how we're going to do it. You could write it as z squared plus 1 and z squared minus 1. That's how it factors. And then this part factors even more. Z plus 1, z minus 1. The first part you can't factor anymore. Now you could set each one of these factors equal to 0, and you could get all the answers to this problem. This way is faster. The reason I'm not going to do it this way is because I'm going to give you problems that don't always factor. And you're going to have to use the method I just showed you. All right, so let's practice going through it and look at the steps. Okay, so first thing is rewrite this equation in trig form. Well, z is your variable. Okay, we don't know what z is. When we write it in trig form, it'll have a radius and an angle, but we don't know what. So let's just call it r cosine theta plus I sine theta. And we're taking z and raising it to the fourth power. By writing it in trig form, we can use DeMoivre's theorem on the left-hand side. Okay, now we have to write the number 1 in trig form. If it's confusing, you're not sure what it is, think of it like this. There's no imaginary part. It's 1 plus 0i. So this should be very easy to find our radius and our angle. Go 1 unit on the real axis. No units on the imaginary. Augustine, what's my radius?
1.
Yeah, it's 1 unit right. So it's just 1 cosine. And Kobe, what's my angle if I'm on the positive x-axis?
0.
0. So this one, radius is 1, angle is 0. The numbers don't get too much easier to work with. Okay, use DeMoivre's theorem on the left. So you have r to the 4th cosine 4 theta, I sine 4 theta. Keep the right the same. Now we just have to make the parts match up. That should match up. That has to be the same as that. So you got to find a value for r that makes that happen. And this has to be the same as that. So r to the 4th equals 1. Okay, how would I solve that? How would I get rid of that 4th power on r? James? Yeah, you take the 4th root. Now, if this was something, okay, more complex, to take a 4th root on your calculator, you press 4, you go to math, it's the 5th option, and then you type in what you need to take the 4th root of. But I'm looking for what number times itself 4 times gives me 1. And I'm looking for a positive number because it's a radius, it's a distance. So negative distance wouldn't make sense. Okay, so r is 1. Okay, now I need my angle. This is the part that's going to give me multiple answers. So 4 theta is equal to 0 degrees, or anything that's coterminal with it, plus 360k. Now I'm finding a, let's see, 4th root. So I'm looking for 4 answers. What are the 4 values that I'm going to let k be? Yeah. 0, 1, 2, 3. So now just write out what this all says. Okay. In fact, one other thing we could do here is we could divide each side by 4, just to get theta by itself. 360 divided by 4 is 90. Okay, so my first answer is r cosine of, fill in 0 for k. My second answer, r stays the same again. R is going to be the same for all 4 answers. Now let k equal 1. 90 times 1, now my angle's 90. Next answer, r is 1. Now we're going to let k equal 2. 90 times 2 gives me 180. Last answer, let k equal 3. 90 times 3, 270. Now, this problem is special because all these angles came out to quadrantal angles, so we'll simplify them. It really helps if you just have all the quadrantal angles memorized for sine and cosine. Cosine of 0 is 1. Sine of 0 is 0. So this time, we're going to have 0 times I. That's gone. And 1 times 1. And we can check each one of these answers by raising them to the 4th power and seeing if we get 1. Okay? Let's check the first one. 1 to the 4th power, yeah. 1 times 1 times 1 times 1, that is 4. We should have 3 other different ones. Cosine of 90, okay, that's going to be 0. Sine of 90 is 1. 0 plus I times 1. I. Okay, if you raise I to the 4th power, do you get 1? Yeah. I times I is negative 1. I times I is another negative 1. And then negative 1 times negative 1 is 1. Okay, so that to the 4th power is 1. So that one works. Let's check this one. Okay, cosine of 180, negative 1. Sine of 180 is 0. Imaginary part's gone. Got 1 times negative 1. Negative 1 times negative 1 times negative 1 times negative 1. Yep, that's 1. So that's our third answer. And our last one, let's see. This part is 0. Sine of 270 is negative 1. So we get negative 1 times I. And if you multiply negative I times negative I times negative I times negative I, you get 1. So these are the 4 answers you're looking for. Notice the complex answers occurred in conjugate pairs. Okay, that will always happen. It's impossible to have, for example, an odd number of complex roots. You'll always have an even amount. Okay, any question on that? Let's try proving that this is an 8th root of unity. In other words, I want you to prove that if you took all the 8th roots of 1, there would be 8 different answers. This is one of them. How can you prove that this is an 8th root of 1? It's like if I said to you, prove to me 3 is the square root of 9. It's the same idea. How do you prove that? Yeah?
Would you just do it to the 8th power?
Yeah, and what are you hoping to get?
1.
Right, if you raise this to the 8th power and you get 1 as the answer, then this is the 8th root of 1. At least it's one of the 8 answers. Well, what's nice is when you raise this to the 8th power, the radius is 1, so you don't need to worry about that. And when you multiply the angle by 8, it cancels in each spot. So you get cosine 2 pi plus I sine 2 pi. Want to make it even easier? It's the cosine of 0, I sine 0. 2 pi is the same as 0. Okay, I'm doing this in radians. Cosine of 0 is 1. The sine of 0 is 0. I times 0 cancels out, and you get 1. So by raising this to the 8th power, you just proved that this is an 8th root of 1. How would you get the other answers? Well, we'd have to go through the whole process. But that's not what this problem is about. Okay. Any questions how I just proved that's an eighth root of 1? Generally, that's a little faster to do than the other types of problems. We've done a lot with 1 and negative 1. Let's try something different. Let's try the cube roots of negative 8. Okay, so what would be the equation I would set up that I need to solve? Z to what power equals what? Yep. Yes. If you can solve that equation, you can answer my question. I need you to solve z cubed equals negative 8. The first step is to rewrite the left and the right-hand side in trig form. Okay, so we're going to have, I'm going to do two things at once. I'm going to rewrite the left-hand side in trig form and use DeMoivre's theorem. So I'd have r cubed cosine. Brianna, what would my angle be? So it'll just be a number and then theta. So think about the power you're raising to is what? 3. So you're multiplying the angle by 3. Cosine 3 theta. Okay. Any question on that? Is that too confusing to do both steps at once? Okay. The step before it would have been r cosine theta, I sine theta, all to the third power. Then you would have cubed the r and tripled the angle. Okay? So that's your left-hand side. Now the right-hand side, negative 8. There's no imaginary part to that number. We just went left 8. So my radius is 8. And my angle, well, Victoria, what's my angle over here? It's a quadrantal angle. We just have to remember the 0, 90, 180. Yep. Good. So you got 180. So now we've rewritten z and cubed it in trig form. And we've rewritten negative 8 in trig form. The negative is taken care of by the 180. You've told me the angle. I know 180 goes left. That's negative. Now this will match that. This will match that. So r cubed equals 8. So my radius is 2. And that's going to be 2 for every problem. I'm going to have 3 answers. And my angle, 3 theta, is going to equal 180 plus 360k. My suggestion would be divide everything by 3 right away to get theta by itself. Now we got to decide on the 3 values we're going to let k be. Cole, what will I let k come out to? Not sure. How many different values am I going to get in this problem? 3. We're going to get 3, so we just have to decide on the 3 numbers to let k be. Yeah, start at 0. Keep going until you get as many as you need for answers. 0, 1, 2. 3 answers. Okay, so the first answer is going to be 2 cosine of, fill in 0 for k, get 60. So this was k equals 0, k equals 1, 120 plus 60 is 180. In the last case, k equals 2. 120 times 2 is 240, plus 60 is 300. I'm not going to do these out. We'll leave them. Those are your three answers in trig form. If they wanted it done out, take the cosine of 60, multiply it by 2. Take the sine of 60, multiply it by 2. You have to distribute that number to each one. The second one is going to come out very nice. It's a quadrantal angle. Okay, any questions on that one? Okay, so the last one, we'll set it up. I don't think we're going to get through all 5 answers, but at least if you can see how to set it up, the last part is just letting k equal 0, 1, 2, 3, 4. Okay, anybody tell me, what am I going to put on the left-hand side? It's going to be r to what power? Andy?
R to the 5th.
Good. R to the 5th. Cosine, can you tell me my angle too? Think about DeMoivre's theorem and you're raising something to the 5th power.
5 theta.
Good. 5 theta plus I sine 5 theta. This just eliminates having to write a step and then rewrite it to do this one step. So you raise r to the 5th, multiply the angle by 5. Now 1 plus I. Quickly, we need to change that into trig form. Well, we have sides of 1 and 1. So the hypotenuse is square root 2. Since this is an isosceles triangle in quadrant 1, the angle is 45 degrees. If I didn't know that, do inverse tangent of y over x. Okay, so that's the setup. Now we need r to the 5th to equal that. We need 5 theta to equal 45 degrees. So the first part relies on a little bit of algebra 1. If you take the square root of something, that's the same as raising it to the 1/2 power. That's from algebra 1. Also from algebra 1, if we raise a power to a power, we multiply. So I'm going to raise this side to the 1/5. I'm going to raise this side to the 1/5. The reason I'm going to do that is because look what happens if you multiply 5 and 1/5. You get 1. So now I just have r to the 1st. And on this side I get 2 to the 1/10, which is the same as the 10th root of 2. In algebra 2 you talk about fractional exponents and how to rewrite them as roots. Okay, so can't go through that right now, but that's how I'm going to leave it. The 10th root of 2. So for all 5 of my answers, which I'm just going to write out the first one, they're all going to be 10 root 2. And my angle, it's 5 theta equals 45 plus 360k. Divide everything through by 5. That'll get theta by itself. And theta is going to be 9 plus 72k. It's a 5th root, looking for 5 answers. 0, 1, 2, 3, 4. Here's your 5 answers. Now you just have to write each one. So the first one would be let k equal 0. It'd be cosine 9 degrees, I sine 9 degrees. I'll do one more just so you have it. Same radius. Let k equal 1. 72 times 1 is 72, plus 9 is 81. And then you still have to do k equals 2, 3, 4. Okay, but that's how you find complex roots. Once you go through it, it's not too bad. It can take a while, but it's the same thing every time. All right, so the homework is on page 458. And it's 2 through 5, 7 to 12, 17, and 25 to 28, and 34 and 35. So we'll take a look at that tomorrow, and we'll also start vectors tomorrow.